Right, good morning. We are looking at the trigonometry questions of the November 2017 question paper in this video for grade 12. So let's jump in. We're going to start with question 5. The three questions of 5, 6, and 7. So the first question here, 5.1, given sine A minus 360 cos 90 plus A, cos 90 minus A tan minus A. Simplify the expression to a single trigonometric ratio. Okay, so this uses reductions. I'm going to quickly just draw my reduction diagram here. 0, 90, 180, 270, 360. And keep in mind that I go bigger that side and smaller this side. And so 0 plus theta will lie in quadrant 1, 90 plus theta, quadrant 2, 180 plus theta. So I go plus this side minus that side. And just keep in mind your cast diagram where the ratios are positive and negative. Okay, so if I start with sine A minus 360 cos 90 plus A over cos 90 minus A tan minus A. Okay, I have A minus 360. A is an angle in quadrant 1. Minus 360 goes around this side. If I make a complete turn minus 360, that just lies in quadrant 1 again, which is then sine A. Or you can think of this as I can add and subtract 360 to any angle without changing it. So if I add to A minus 360, add 360, I have A. 360 minus 360 will fall away, so it's just sine A. Cos of 90 plus A, so 90 plus in this direction, 90 plus A is quadrant 2, where cos is negative. So this is going to be negative, but also change it to sine A at 90 to 70, you must change. Okay, so 90 minus A, 90 minus this direction. So 90 minus A is quadrant 1, where cos is positive. So this is changing to sine A, but it's positive. And tan negative A, 0 minus A is quadrant 4. So this is tan in quadrant 4, which is negative tan A. The sine A is cancel and negative over negative is positive. So I have here sine A over tan A. Or I can write this as sine A divided by tan, which is sine A over cos A. And to divide with fractions from primary school on, I can multiply with the reciprocal. So I change that to cos A over sine A. The signs can cancel, leaving me cos A over 1 or cos A. Okay, that's question 5.1. Question 5.2. In the diagram, the point P, which is 3t, is a point on the Cartesian plane. The point P, 3t, is a point on the Cartesian plane. The length of OP is root 34, and HOP, that angle is beta. That's a reflex angle. Without using a calculator, determine the value of t tan beta cos 2 beta. Okay, so I'm going to start off by just completing this diagram properly. So I have, there is my triangle, that's my beta. This is root 34, and then if that is the point 3t, the x is 3, so that length there is going to be 3, and the y is t, which I can see as it's going down is also going to be negative, and I just want to mark that in there just to remind myself. Determine the value of t. I can use the theorem of Pythagoras. T squared is root 34 squared minus 3 squared, which is then 34 minus 9. And that is 25. So t is going to be plus or minus 5, but since I already reminded myself there, it goes down, so it must be negative. T is negative 5. Okay, that's 5.2.1. 5.2.2 is determine the value of tan beta. Tan beta is opposite negative t over adjacent 3. There it is. And since t is, I have that 5, this is going to be negative 5 over 3. 5.2.3 cos 2 beta. Now, my diagram here has an angle beta, so I'm going to change this using the formulas. You can use cos squared minus sine squared, 2 cos squared minus 1, 1 minus 2 sine squared. Either one will work. I think it doesn't really matter. I'm just going to go with 1 minus 2 sine squared beta, which is then 1 minus 2 sine beta is going to be negative 5 over 34, negative 5 over root 34, and I want to square that. So I have 1 minus 2 times negative 5 squared is positive 25, root 34 squared is just 34. So I have 1 minus 50 over 34, and this is then 34 over 34 minus 50. So 34 minus 50 is negative 16 over 34. I apologize for the background noise. Right, that's question 5.2.3. Then question 5.3.1, prove that sine A plus B minus sine A minus B is 2 cos A sine B. This is a fairly routine question. So I'm going to have sine A plus B minus sine A minus B. If I start with the left hand side, expand this into sine A cos B plus cos A sine B minus sine A cos B, sine A cos B minus cos A sine B. I just put this in brackets, the second expansion, because I must now still multiply in this negative there. So I have sine A cos B plus cos A sine B minus sine A cos B plus cos A sine B, and then I'm going to add like terms. So sine A cos B minus sine A cos B, this is the same. 1 minus 1, 0. And cos A sine B plus cos A sine B is 2 cos A sine B, which is my right hand side. Okay, that wasn't really difficult. 5.3.2, without using a calculator, find that sine, or show that sine 77 minus sine 43 is equal to sine 17. So I want to try and use this formula now. So I'm trying to think of something, two things that I add that gives me A plus B, and that I add A plus B, that's 77, and the same A plus B, if I subtract them, must give me 43. And then cos A sine B must be equal to sine 17, which to cos A sine B, I want to simplify this. Okay, so I'm going to try and use a special angle, so something like 60 plus 17, which is a good idea, and 60 minus 17. So I'm going to start with that left hand side. I think I might actually need to turn the page. So I'm going to start with replacing the 77 with 16 plus 17, minus sine of 60 minus 17, and I actually don't need to expand this. I already simplified this to cos A sine B, and my A is 60 and my B is 17. So I can just replace this now to cos A sine B. I'm just saving a bit of time there. And then special angle for cos 60, however you do that, is a half sine 17. 2 times a half is 1 sine 17, which is my right hand side. Okay, right, that's fairly simple. Okay, so that is question 5. We can look at question 6. I'm just going to turn the page over here. Alright. Question 6, trigonometric graphs. So in the diagram, the graph of cos 2x is drawn from minus 270 to 90. Cos 2x means the period of the graph has been shrunk by a factor 2. So instead of from 0 to 360, the graph is going to make that cup that it makes from 0 to 180, and also from 0 to negative 180. You see it's been made smaller by a factor 2. Draw the graph of gx is 2 sine x minus 1 on the grid. I'm still going to draw it on here. 2 sine x is going to have a sine graph that's been stretched. Instead of between minus 1 and 1, it's going to go to 2 and minus 2. That stretches the amplitude. Minus 1 is going to move it down. So instead of minus 2 and 2, now it's going to go down to minus 3 and 1. So a normal sine graph starts there. It's going to go to 1 there at the top at 90. There. And it's going to go at minus 90 to negative 3 there. In the previous video on the 2016 paper, I showed you a different method of also doing this if you struggle to implicate the stretches. Right, there's my graph. Stretched factor 2 amplitude and moved down 1. There's my graph. If you struggle to implicate the changes from the formula and just draw that, something else you can do is to use that table. If you didn't watch the previous video, you can quickly just go back to that and watch that. I'll link it down below. Okay, then, there's my sketch. All of the turning points intercepts with the axis. I've shown that. Okay, let A be a point of intersection of the graphs of f and g. Show that the x-coordinate of A satisfy the equation that sine x is minus 1 plus root 5 over 2. Okay, so there is a point of intersection and there is a point of intersection. I don't know if it will matter which one I take, but I'm gonna start my there. Okay, so point of intersection I can get by taking fx is equal to gx mathematically. So 6.2, I'm going to take fx, which is cos 2x, is equal to gx, which is 2 sine x minus 1. Okay, and I want to make this there, use the formula. I'm going to use the formula 1 minus 2 sine squared x because I already have a sine in the equation to keep the ratio sine now. And then I'm going to take everything to that side. So I have 0 on this side. I have 2 sine squared x plus 2 sine x. Minus 1 is minus 2, and I can divide with a 2 just to make it a bit simpler. I have sine squared x plus sine x minus 1. Okay, this doesn't really factorize. With normal factorize rules, there's no factors of 1 that's going to give me 1. If I subtract them, so I'm going to just use the quadratic formula here. Sine x is equal to my quadratic formula. It's on your formula sheet. Minus b plus or minus root of b squared minus 1, minus 4, sorry, a, which is 1, c, which is negative 1, over 2a, which is also 1, and then that gives me, oh, I think I must not use a calculator. Sin x is equal to minus 1 plus root 5. It doesn't say no calculator, so I'm sure it's fine. Minus 1 root plus root 5 over 2, or sin x is equal to, and then there I'm going to subtract minus 1 plus root 5 over 2. It's the same thing. Oh, that minus is in front, which is actually going to make it minus 1 minus root 5. Okay, it's the entirety is negative. Okay, so I wanted to show minus 1 this one, which that one is not applicable, but that is then my answer. Okay, and 6.3 hence. Calculate the coordinates of the points of intersections of graphs f and g for the interval. So I have the two coordinates there. The one is going to be this one. Let me just get the general solution here now. So if I have that, I have a sine x reference angle. X is shift sine of my answer. Whoopsie. Shift sine of, I actually prefer to work with the decimal form, minus 1 plus root 5 over 2. So x is 38,17, or x is, I just want to do that one as well. If I put the minus there in front, it gives me a math error. Okay, so that one is not applicable anyways. Okay, so that one is definitely not applicable. Okay, so there is that. Since sine is positive, you can actually check that minus 1, it looks negative because of that, but if you just quickly look at the decimal form of this is actually something positive, right? So since sine is positive, I'm working in quadrant 1, which means x is 38,17 plus k 360, or in quadrant 2, x is going to be, there's my reference angle, is 180 minus the reference angle is 141,83 plus k 360. Alright, to place this in quadrant 3, I take 180 minus the reference angle, and now I want to produce the coordinates of those two. So the coordinates of this one is going to be 38, the x value. It's going to be 38, and the corresponding y value, which you'll find now. I just want that cutting point as well. Oops, sorry, this one is going to be 38. I just want that one as well, and that one I'm going to get by taking 141.83, which I have here now, subtract 360. It's minus 218, you see. Because this means I can add and subtract 360 to produce other angles. That 141 cutting point will lie on this side somewhere off the graph, but that point I can get by taking the 141. So my coordinates of the point of intersection, let's call them, let's just list them like that, is going to be, there's my set of coordinates, is going to be at 38,17. I need to find that as well. and at negative 218,17, and I need to find that. Now to find the y values, you can just substitute this into either the f or the g function, because both, it's a point of intersection, so both functions goes through that point at the same place. So I can simply use f, which is cos 2x. Cos 2x as 38.17 is going to be 0,236, so 0,24, and if I make it that one, negative 218.17, it will produce the y value 0,236, so 24. Oh, it's actually the same. All right, so there is, I can see on the sketch as well that on the same height, these two cutting points. Okay, so there is my cutting points. That's question 6.3. And lastly, we're going to look at question 7. I'm just going to start on a new page. Question 7. 3D, 2D, 3D problems using the sine, cos, and area rule. AB represents a vertical netball pole. Two players are positioned on either side of the netball pole at points D and E. So there's two players standing there, such that D, B, and E are on a straight line. So they're all standing there on the same line. A third player is positioned at C. The points B, C, D, and E are on the same horizontal plane. So, I mean, this is the ground of the netball field, netball court. The angles of elevation. Oh, you can't see the sketch. Sorry. Okay, so there is one player, there's another player, and there's another player, and they are all standing on the same horizontal plane on the ground, and there's the netball pole. Okay, so the angles of elevation from C to A and from E to A are x and y irrespectively. The distance from B to E is k. B to E, that distance there is k. Okay, write down the size of angle ABC. ABC, that angle obviously 90 degrees because it's the floor or the ground and a vertical netball pole. So 7.1. I think they're just checking whether you noticed that, but angle ABC is 90 degrees, and obviously ABD, that is also 90, 90, 90. All right, okay, show that AC that there can be written as K tan Y sine X. Okay, so from this player, that E player, the triangle, I have that length is K, and AB, I can get AB from this because I have the K and it's a 90-degree triangle. So tan Y is AB over K, and from that I can get AB. I want to show that AC is something. Then I have AB in this triangle. I have AB, and I can use AB over AC is sine of x. So I'm going to start in that triangle where I have more information. 7.2, I can say that tan y is equal to AB over k. And then from there I get that AB, if I just multiply the k on that side, is k tan y. Okay, and then I can say in this triangle that sine x is AB over AC. I want to get the length of AC. AB is k tan y, so I'm going to just substitute that. K tan y over AC. And let's just put this over 1 so I can cross multiply. So I have sine x times AC is equal to 1 times k tan y, and then to get the AC alone, I have AC is k tan y over sine x, and that's exactly what I wanted to show. 7.3 now says if it is further given that DAC is 2x, DAC, so now I'm working in this triangle. It's a sort of a slanted triangle there between the two players to the top of the netball pole. So that DAC, that angle there is 2x, and AD is equal to AC, which I worked out there now. Show that the distance DC between the two players is 2k tan y. So I think I'm going to work with the cos rule. Because I don't have, if I look at this triangle there, I don't have this angle there between, if I draw in that line there, and I want to work in this triangle there, I don't have that angle or that angle. It's the same, but I don't have it. I have this side and I need that side, DC. So I have three sides and an angle, meaning I can use the cos rule, and I'm going to see where that leads me. Okay, so in the cos rule, a squared is equal to b squared plus c squared minus 2bc cos a. I'm going to use the 2x as my angle and the dc then across from that as this side. So dc squared is equal to b and c squared is then both going to be that. So b squared k tan y over sine x squared plus k tan y over sine x squared minus 2, and b is also that and c is that, so k tan y over sine x times itself. B and c is the same, and then cos a is cos 2x. Okay, so I want to get the value of DC anyways. Okay, so I need to simplify this a little bit. Okay, so I have this squared plus this squared, it's the same thing, so I'm just going to write that twice. 2k squared tan squared y over sine squared x minus 2k squared tan squared over sine squared x times cos 2x. And now I think let's take out the this thing as a common factor. So I have 2k squared tan squared y over sine squared x as a common factor. Then here, if I take that out, the 2 and that, I'm left with 1, minus, if I take that out, I'm left with cos 2x. And since there's a sign which I don't want, if I look at where I'm going with this, I want to go 2k tan y as my answer, 2k tan y. So 2k tan y, something there. There's a sign which I don't want there. And here I have an option of replacing with something cos and sine, something only sine and something cos. I want to cancel the sign, so I'm going to go with the option there. I'm going to multiply that in 2k squared tan squared y over sine squared x, and then I'm going to make this 1 minus 1 minus 2 sine squared x, like that, and then 2k squared tan squared y over sine squared x. 1 minus 1 is 0, and minus times minus, if I multiply this in, it's negative 1, and plus 2 sine squared x. The 1 minus 1 is going to fall away, so I'm just left with 2 sine squared x. The sines, if I put this over 1, the sine squared x can cancel. 2 times 2 is 4, so I have 4k squared tan squared y left. This is dc squared. So then dc is going to be the square root of 4 is 2 square root of k squared square root of tan squared. So DC is 2k tan y, and that is what I wanted to have. Great. Okay, so that is the trigonometry questions for November 2017, and I'll see you in the next video where we're going to look at 2018.